Hello everyone and welcome back. So right now we are talking about the precipitation sequence in different age hardenable aluminum alloys. And in the last lecture, we talked about the precipitation sequence in the 8000 series aluminum lithium alloys. We have only two phases here, delta prime and delta. Okay. Al3Li is the delta prime and ALLi is the delta. And Al3Li has a ordered structure, and therefore the main strengthening mechanism in this case is order strengthening. But one important thing that you would have seen is the fact that these kind of precipitates can be sheared by dislocations, giving rise to a low ductility and fracture toughness. Okay, so that is the important thing to note here about these precipitates. Okay, and as I said, that is what has actually rendered these alloys unusable in many applications. What people thought could be potential areas for these alloys. Now let us have a look at some of the alloys in this series. The one which really showed attractive properties is this one, 8090. Having a composition of 2.6% lithium, 1.9% copper, some amount of magnesium, and little bit of zirconium. So here you can see you have additionally copper and magnesium apart from lithium, right? So therefore, these two atoms can also take part in forming the precipitates, and therefore in such alloys, apart from the delta prime precipitate, you will have one more precipitate, which is S prime, that contains both copper and magnesium. Right, so you have additional contribution coming from these S prime precipitates apart from the delta prime. And another advantage that you have, this kind of precipitate, the S prime precipitates, they cannot be shared, unlike the delta prime precipitates. So here you can expect some improved ductility, but even then, it was difficult to overcome the fracture toughness problem. The fracture toughness value, for example, the K1C value, if you see, this is around 40. And the yield strength is around 430 MPa. So these are actually high strength alloys. Only difficulty, as I said, is the fracture toughness and the ductility. And the density is also low, as I said before. Much lower than pure aluminium. Okay. One more alloy in this series is the 8090, 8091. 8090 we already talked about. In fact, this one is 8090, 8091 in terms of the composition, if you see. And 8090 is having little less copper. Although the lithium remains almost same, but copper here is around 1.3%, unlike the 8091 where it was 1.9%. Magnesium also remains almost same. So does zirconium. And these properties that I talked about, these belong to 8090. And for the 8091, if you look at the properties, it is little higher because you have little more copper. So the strength is 490 MPa, but the fracture toughness is lower. From 40, it comes down to 30. All right, and this will also bring us to the end of this particular topic that we have been discussing about in last few classes, this precipitation hardening topic. But before we close this topic, it will be good to have a look at the morphology of different precipitates that we talked about. Okay. So in the heat treatable alloys, we have 2000 series, 6000 series, the 7000 series and the 8000 series. Okay. And each of these alloys have a particular strengthening precipitate, which will also have a particular morphology. So let us have a look at the morphologies of different precipitates in these alloy systems. So in the 2000 series aluminium copper alloys, the strengthening precipitate is CuAl2 or Al2Cu, which is also known as theta prime, and this is how the morphology of this precipitate is. So this is how this particular precipitate will look like under a transmission electron microscope. Okay. Now in the 2000 series alloys, sometime you also have some amount of magnesium. So if you have magnesium, apart from the theta prime precipitate, one more precipitate forms, which is known as the S prime precipitate or this Al2CuMg. Okay. So we have seen the morphology of the theta prime precipitate, which is on the left hand side image over here. And on the right hand side, apart from this theta prime precipitates, you would also see some other precipitates appearing as needles, which are shown by these arrows, okay, over here. So you can see this needle kind of morphology over here around this area, for example. So these are the S prime or Al2CuMg precipitates. Okay. So these are the precipitate morphologies in the 2000 series alloy. Now let us go to the next one, that is aluminium, magnesium, silicon 6000 series alloys. And if you recall, in these alloys, the strengthening precipitate is Mg2Si. And this is the morphology of these precipitates. So this is how this will appear when looked under a transmission electron microscope. Now let us go to the next one, that is 7000 series alloys. So here we have the 7075 alloy, where the precipitate is eta prime, and this is how they look like. These two TM images over here show the morphology of the eta prime precipitates. So here the precipitate volume fraction could be different depending on the aging conditions or the actual composition of the alloy, but the morphology is going to remain the same, as you could see from here. And then next we have this aluminium lithium 8000 series alloy. So this is an example of this 1890 alloy having aluminium, lithium and copper. So the strengthening precipitate here is delta prime, as you might know, and the morphology of such precipitates is spherical, as you could see from these two images over here. So here also the content or the volume fraction of the precipitate is different in these two images, but the morphology is same, and that is spherical. Okay. So these are the different kinds of precipitates that you have in these heat treatable alloys, and this is how they appear in morphology when looked under a transmission electron microscope. Right, so with this we can close this particular topic. We can conclude this topic. Yeah, but still we are not done with the strengthening mechanisms, because there are few more strengthening mechanisms that we have for aluminium alloys. Especially for the non-heatable alloys, you do not have a mechanism like what we have discussed just now, the precipitation hardening, right? Because there you cannot form precipitates. So for those kind of alloys, then what could be the other mechanisms? So we must have some other strengthening mechanisms also that we can make use of for the other alloys which are not heat treatable. And that is what we are going to look at right now, and maybe next couple of classes. So we have talked about, if you remember, giving some amount of deformation even for the precipitation hardenable alloys in between or after the precipitation. So that was done to further increase the strength, or to make sure that the precipitates form uniformly, and the dislocations which are generated due to the cold working can act as the heterogeneous nucleation sites, right? So cold working is one mechanism through which you can actually increase the strength also. Okay. So that also becomes one of the strengthening mechanisms, and in the general term, if you want to define that particular mechanism which comes through deformation, that can be defined by this name, strain hardening. Okay, which means you strain the material or deform the material, and through that you harden it. Okay, so that's literally, you can see from here, as the name suggests, strain hardening or work hardening. These two are synonymous. So this refers to deforming the material in cold condition. Cold means a temperature which may be room temperature or some other temperature at which the recovery mechanisms cannot come into play. Okay. Recovery mechanisms means I am talking about the recovery and the recrystallization which can occur for the recovery or the dislocation annihilation process to start. So cold working is the process through which you deform the material and generate additional dislocations to increase the dislocation density, and through that you obtain the strengthening, right? So it has to be done at a temperature where you can retain these dislocations which are generated by the deformation process, right? So when you do that cold working in such temperatures, which may be room temperature also, as I said, it will be referred to as cold working. So this is the one that we are going to talk about right now, and like how we have done before, we will see what is the mechanism through which the strengthening occurs in this case. So looking at a schematic as to what exactly could happen inside the material, this is a schematic for that, just to try and understand what is happening in the material. So this is the initial structure. Let's say you have an equiaxed microstructure like this kind of equiaxed grains, and then this is being deformed to a particular strain at a particular temperature, which is below the recrystallization temperature. And as you deform it, the grains will deform like this. So this is the cold worked structure, right? So this kind of tells you that there are some changes occurring inside the material, and in order to accommodate such strain inside the material, you need to generate a lot of dislocations, right? So the grains will deform, that is for sure, because we are actually deforming it, we are applying some stress to deform the material. But apart from that, it will also activate the dislocation sources, or the Frank Read sources as we call them, and a lot of dislocations will be generated. So you can expect the dislocation density to increase. Okay, and now if you look at the relationship between the strength and the dislocation density rho, it goes by this particular equation that you see over here. Okay, where rho is the dislocation density, and other terms we have already defined before. G is the shear modulus and B is the Burgers vector, and alpha is a constant over here. So when you do the cold working on a material, it generates additional dislocations, as I said, and the dislocation density increases to this level. So in a normal annealed material, you have dislocation density in this range, but when you do some cold working, you can see that it is increasing, the dislocation density is increasing by orders of magnitude. From 10 to the power 4 to 10 to the power 6, it is going to 10 to the power 10 per millimeter square. Okay. So because of availability of higher dislocation density, the motion of other dislocations which are now moving on the slip plane as you deform the material will be difficult, and as a result of that, the strength will increase. Okay, so this is about the dislocation interaction, which results in hampering the motion of dislocations, right? And as a result of that, as I said, the strength will increase, and that can be given by an equation like this, which relates the strength to the dislocation density. Okay, and this is again a plot which shows what happens due to this process as you increase the percent of cold work or the degree of deformation. You can see the strength and hardness increase, but on the other hand, the ductility will decrease. Okay, so this is the effect of cold working on the mechanical properties. Okay, so now we need to understand as to what is the actual mechanism of this strengthening that you see due to cold working given to the material, and that's what we are going to discuss next. But before that, it may be a good idea to go back to the aluminum alloys and see how you can identify, what kind of operation these alloys are subjected to, particularly this non-heatable alloy. Okay, so here also, when they are subjected to cold working for improving the strength, here also you can see some kind of nomenclature through which you can identify what kind of strain hardening operation or what degree of deformation has been given to a particular material. That can be identified by looking at the designation. Okay, so let us talk about that before we come to these mechanisms. So this is with regard to strain hardening of aluminum alloys. and we are going to look at the corresponding alloy designations or tempers. These two we have already seen before, F and O. F indicates as fabricated, and O means annealed, or recrystallized. Now, when you talk about the hardening, this letter H comes into picture, indicating strain hardening, and this will be followed by a digit like 1, for example. So when you see H in the temper, then you know that this alloy has been strain hardened. And to what level or what degree it has been deformed or strain hardened, that you can identify from one more digit which will follow the first digit. Okay, so it will be like this. H12, H14, H16, and H18. So this one that you see over here, this means fully hardened. So 8 indicates fully hardened condition. And therefore the others will accordingly indicate the level of strain hardening. If 8 is 100%, then 2 will be 25%, right? So this is 1/4 hardened. Similarly, this is half hardened, or 1/2, and this is 3/4 hardened. Right, so this is how, with the help of the second digit over here, you can identify the level or the degree of deformation which is given to the material. Okay, and if you find beyond 8, that means if you have a temper like this, H19, that means this is extra hardened. Fully hardened is something where you have a 75% reduction in the cross-sectional area. By the deformation process which is applied. So H19 would indicate that the deformation is beyond 75% reduction in the area. Okay. And then you have H2 temper, like how you have H1. H2 is also there, and this basically indicates strain hardened given first more than the required, and afterwards it is reduced. So first it is extra hardened, and then the strength is reduced to the required level by partial annealing. So that is what H2 indicates. And like in case of H1, you have one more digit to follow. Here also you have the same thing. So in the previous case, the second digit indicates the level of straining or the degree of deformation, but in this case, the second digit indicates the degree of strain hardening which is remaining. Because as I said, it is partially annealed to reduce it. So after annealing, whatever be the remaining level of strain hardening, that is indicated by this second digit. And finally, you also have H3. So here it is strain hardened first, and then stabilized or annealed. And you have similar second digits here also. And in this case, the second digit indicates the strain hardening remaining after the stabilization operation. Stabilization is nothing but heating the material at a particular temperature, typically around 110 to 180 degrees Celsius, to anneal it, so that you can reduce the degree of straining which was given in the beginning, to bring it to the level which is actually needed, right? So the second digit here indicates after the stabilization operation, whatever strain hardening is remaining. Okay. So with that, we can finish this lecture, and the rest of the things that we have will be taken up in the upcoming lectures. Thank you.